Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over the temperature dependence of the equilibrium constant. Okay, let's get into this. So first, let's point out that in a previous video we saw that the standard free energy change of a reaction is going to be equal to the negative RT ln of K, where R is the ideal gas law constant, 8.314 joules per mole Kelvin. And that's going to be multiplied by the temperature in Kelvin and then multiplied by the natural law of the equilibrium constant. So we saw before that the change in the free energy, the standard free energy change of a reaction is related to the equilibrium constant of the reaction. And so in a previous video, we also had this equation here that the standard free energy change of a reaction is equal to the standard enthalpy change of a reaction minus the temperature multiplied by the entropy, the standard entropy change of a reaction. So we have both these equations where the standard free energy change of a reaction is equal to these two things. So by logic, if this is equal to both of these and these are equal to each other, so we can set those equal. And so we take these two and add them, make them equal to each other. So we have the negative RT ln of K is equal to the standard enthalpy change of reaction minus T delta S of the reaction. Okay, so now that we have these equal to each other, we can manipulate the equation and get it into a couple of forms that we are familiar with. So if I take the negative RT here and divide both sides by the negative RT, I'll get ln of K by itself. So I have ln of K. And so this is then going to be divided by negative RT. And then this is going to be divided by negative RT as well. So that becomes a positive. So negative divided by negative becomes a positive. And then I get T delta S of the reaction over RT. And then the T's are going to cancel out here. And then what I can do is I can kind of manipulate this a little bit more and get it into what is called the point slope form. That is your y equals mx plus b. So if I bring this T out, so the temperature here is a variable. So if I bring this out here and I have 1 over T, so there's my 1 over T. All I've done is I've kind of brought it out. So I have the negative delta H of the reaction over R multiplied by 1 over T, and then plus the delta S of the reaction over R. And so you can see that it's in the point slope form where Y is my ln of K. The slope is going to be the negative delta H of the reaction over R. My X value is going to be 1 over T. And my slope, my Y-intercept is going to be delta S reaction over R. And so this, when I plot my data, so if I have data of the equilibrium constant related to temperature, then what I can do is I can calculate the 1 over the temperature, and I can calculate the natural log of K, get that data, and then I can plot a straight line. And so this will give me a straight line where in the form of y equals mx plus b, where the slope of the line is going to be negative delta H of the reaction over R. So then I can find the delta H of the reaction, the standard enthalpy change of the reaction from my slope. And then from the y-intercept, I can find my delta S of the reaction. So I can get thermodynamic information, delta H, delta S, from my straight line. And then from the line equation of a line, if I do a best fit, and then I tell the computer or the Excel program to give me the equation. So that's the point slope form. So that'll be useful. So one thing to keep in mind, as I mentioned here, that we would only be able to get this over relatively what's the word I'm looking for? I wrote it down here. Um, over a relatively limited temperature. The reason for that is because, as we saw in a previous video, the delta S of the reaction and the delta H are both slightly temperature dependent themselves. So we can only use this equation over, again, a slightly limited range of temperatures. So the other form I want to point out is also the 2-point slope form. The 2-point form. And this is where you could use this if you, let's say, for example, if you measured the reaction at two different temperatures and therefore you got two different equilibrium constants, then you could take that data and plug it into this form where you've got the two equilibrium constants at the two different temperatures. You plug those in to the equation and then you can find your delta H of the reaction. Okay, so this is some good equations. Remember, useful equations to remember with regard to the temperature dependence of the equilibrium constant. So you can see that here. So you have the equilibrium constant here is related to temperature. It's dependent on the temperature. Change the temperature, you change the equilibrium constant. Okay. So I hope this was helpful. If you enjoyed this video, if this was helpful in any way, then please, by all means, like my video, share my video, hit that like button right there, please. Also, subscribe to my channel, hit that notification bell so you can be notified about other videos. When you hit the notification bell, make sure you hit all so that way you can see all my videos. And also put a comment down in the comment section. Let me know what you think. Ask me questions. I love to hear from you. Thanks for joining me. Have a great day.